Okay, here's the agenda for today's lecture. First, I will give an introduction on energy transition, what is the role of hydride-based materials can play, and after I will go deeper in the description of metal and complex hydrides, and finally give a short conclusion. Okay, I would like to start the introduction with this well-known graph representing the so-called Huber peak oil. Indeed, owing to the finite resources of oil, geologist Marian King Hubert has predicted an inevitable decrease of oil production. Hubert placed this peak in 1971. However, for some geostrategic reasons, some states have underestimated their feedstock. Furthermore, because now oil is a very profitable market, new unconventional sources have been explored, such as deep offshore or schist oil or sand oil. Therefore, the experts expect the peak now in 2030. So why I like to show this graph? It's because it's been a long time that we know that we will inevitably go toward an energy transition, but not much has been done so far. So these graphs also show the necessity to the energy transition with the ever-growing energy demand alongside with the exponential worldwide carbon dioxide emission. It's interesting to note that today only a small fraction of energy is produced carbon dioxide free. So it demonstrates that the energy transition cannot be fast. And to reduce carbon dioxide emission, efforts in decreasing our energy consumption must be done. So because we are going to dramatic consequences for our environment, and now we are in the emergency to substitute our fossil fuel by renewable energy. And if possible, carbon dioxide free. So what is the definition of renewable energy? So it's an energy derived from natural processes in perpetual renewal to prevent phenomena like the Hubbert peak oil, but it is not necessarily CO2 free, such as biogas or biofuel. Therefore, we need to focus our attention on sources like sun, wind, or water. Today, we have made some enormous advances in converting these sources into energy, like photovoltaic or wind turbine. But owing to their intermittent nature, we need to manage the fluctuation in time and space. The typical example is the sun, producing a maximum of energy at noon, when we don't need it. And in all countries, we are not even for solar or wind energy, derived energy. So the development of efficient method to store this excess in energy is needed to be used in due time and space. To this end, several methods are available, and I picked these three: hydrogen storage, heat storage, electrochemical energy storage, because the hydride-based material find application for the three technologies. But I will focus more around the hydrogen storage with some example for the other method. So remember, we need to manage the fluctuation in time and space of the energy produced from renewable source. And one way could be to use this excess in energy to produce hydrogen, but to be carbon dioxide free, the best way is to produce it from water electrolysis, which consists of splitting water into hydrogen and oxygen by electrolysis. Following these electrochemical reactions, when produced, the hydrogen must be stored and transported to be used in due time and place. And thanks to a fuel cell, which is the reverse electrochemical reaction of water electrolysis, we can produce electricity. So even though some progresses must be done in electrolyzer and fuel cell, here I will focus my talk on the storage aspect, because the storage dictates the amount of energy you can store per unit of mass and volume. Indeed, this is the main roadblock for energy storage today, which is how much energy you can store in a light material and in a small volume. Here are some pros and cons of hydrogen energy as energy vector. In the pros side, it's a very light fuel, which is perfect for mobile application. It's non-toxic, very abundant, but unfortunately only combined with other elements such as in water or hydrocarbon. It is carbon dioxide free energy vector if it's produced from water. Its gravimetric energy density is 3 times higher than a hydrocarbon. But in the cons side, because it's a gas, it has a low volumetric energy density. But if we find a way to compact it, it can increase. It is highly flammable and explosive, which had led to very unpopular. Because of some spectacular accidents, such as the Hindenburg or the Challenger explosion. And this is, in my opinion, the main drawback of using hydrogen as energy vector. Therefore, some solution must be found to solve this problem. So here are a few numbers about hydrogen, always useful to know. So to run 400 kilometers with a standard car, we need 24 kilograms of gasoline, 8 kilograms of hydrogen when it's used in a combustion engine, and 4 kilograms of hydrogen, just 4 kilograms of hydrogen if it's used with a fuel cell. So the volume of 4 kilograms of hydrogen in ambient pressure and temperature is 44 cubic meter, which is huge compared to only 0.03 cubic meter for 24 kilograms of gasoline. That is why we need to find an efficient, secure, and compact way to store hydrogen. But how to store hydrogen? So two methods are envisaged. The physical-based method, which is the classic way to store gas, and the more mature technology, which is the pressurization and the liquefaction. These two methods are already developed, but for the gas storage, it must be pressurized at 700 bar. So even though a lot of security tests are performed on this kind of tank, one accident of 700 bar of hydrogen is enough to give up this technology. Concerning the liquid storage, the temperature must be kept at minus 253 degrees centigrade, which is very complicated and may also raise some safety issues. The second method is material-based method, consisting of storing within a material which discard the security issues, because hydrogen is not in the gas phase anymore and can lead to higher storage capacity because it's more compact. And among the different strategies, I will discuss only about the hydride-based material, metal, and complex hydride. So as I said, solid-state storage allows to store higher amount of hydrogen in a smaller volume. And for some hydride, as complex hydride with higher gravimetric densities and physical methods. So this graph here map the different methods to store hydrogen as a function of their gravimetric and volumetric densities. So for high energy storage density, one wants to target this area of the graph. And as it can be seen, metal hydride in blue and complex hydride in red possess much more energy density than lithium-ion battery, or if you store hydrogen in a compressed or in a liquid state. So I'm speaking about hydride-based material from the top of my pitch, but some of you may don't know the definition of a hydride. Here it is. So if a hydrogen carries the negative charge, it is denominated as hydride. On the opposite, if it's carrying the positive charge, it's called protic hydrogen. And because hydrogen has an intermediate electronegativity here, it can form very versatile bonds with different elements. For instance, when it's bound with a very electropositive element such as alkaline, it will be highly negatively charged with a stable ionic bond. With transition metal, hydrogen will carry negative charge but will form a pseudo-metallic bond in the metal hydride. Finally, come the elements with close electronegativity to hydrogen, so they will covalently bond, and if electronegativity of the element is a bit lower than hydrogen, it forms a complex hydride. While if the electronegativity is a bit higher than hydrogen within the material, the hydrogen is called protic hydrogen. Okay, now the definition given, let's have a look about metal hydride for energy storage. So a metal hydride is a metal which can absorb hydrogen when it's in contact with hydrogen gas and can reversibly release it at a given pressure and temperature. It's called the chemistry option. And pressure and temperature at which this process happens is related to the thermodynamic of the hydride. And in terms of research, it consists of finding the optimal formulation to store high amount of hydrogen in mild condition of pressure and temperature. So the chemisorption is a process happening in several steps with multiple activation barriers, and the driving force being the stability of the metal hydride. So far from the surface, here, the potential of hydrogen molecule and two hydrogen atoms are separated by the dissociation energy, which is of hydrogen, which is around 436 kilojoule per mole. So the first attractive interaction here is the van der Waals force when the hydrogen approaches the surface, and it's in the physisorb state. And the energy of the bond is about 10 kilojoule per mole. Closer to the surface, the hydrogen has to overcome a first activation barrier for dissociation and formation of hydrogen metal bond. And the height of the barrier of the activation barrier depends on the surface element involved. Hydrogen atom sharing the electron with the metal atom at the surface area then is in the chemisorb state, and the energy of the bond is around 50 kilojoule per mole. And in the next step, the chemisorbed hydrogen jump into the subsurface area here and go through the sublattice of the metal host to form the metal hydride, and follow by a nucleation and growth process to form the full metal hydride phase. So all this process is driven by the thermodynamic of the metal hydride. And to find the thermodynamic parameters, we perform what is called a pressure composition isotherm. So it consists of following the hydrogen composition here as a function of the pressure. Okay, so by increasing the pressure, the hydrogen starts to dissolve slightly in the alloy, forming a single phase solid solution, and the pressure increase. At this point, here, the metal hydride starts to grow into the alloy. And so, because we are in the biphasic state with hydrogen gas, the Gibbs phase rule gives us that only one variable can be independent. Therefore, at a given temperature, the other variables, such as the pressure, are fixed. That is why we have the so-called plateau pressure or equilibrium pressure. Okay, when the metal hydride is formed, we end up with another solid solution, so in a single phase state, where the alloy is in the solid solution of the hydride and the pressure is allowed to raise again. So during is allowed to raise. So at equilibrium pressure, the Gibbs free energy is then just a function of one parameter, the temperature. From this one can derive the frequently used Van 't Hoff equation, which is a linear relationship between the natural logarithm of the equilibrium pressure and the inverse of temperature, allowing the determination of two important thermodynamic parameters, the enthalpy and the entropy. And we just need to perform this PCI experiment at different temperature and report on the graph the natural logarithm of the equilibrium pressure as a function of the inverse of temperature. And we will have the enthalpy and the entropy. So the thermodynamic of metal hydride system can be tailored using intermetallic compound. Indeed, stability of the intermetallic hydride should be nor too high, otherwise the desorption temperature would be too high, nor too low, otherwise the chemisorption would not happen. So to find the optimal composition of intermetallic RMN, the metal R electropositive should form a stable hydride, whereas the metal M should not. And interestingly, there is some defined ratio that have been found to form a stable hydride. And here is an empirical rule which can serve as a guide to adjust the stability of the intermetallic hydride. Here's the periodic table, color-coded, representing the stability of the monometallic hydride. And the stronger is the red color the more stable is the hydride, and the stronger the blue color, the weaker is the stability of the hydride. So we can play with this, all these elements to finally modulate the stability of the intermetallic hydride. A lot of work have been done in this sense, and hundreds of intermetallic hydride have been reported. Here are some examples. In our lab, a lot of work have been done on the system lanthanum nickel, which possesses a rich phase diagram with numerous intermetallic compounds with defined composition. But they are not all interesting for hydrogen storage, most of them forming two stable hydrides. This is a perfect example to illustrate what we have just seen about mixing a stable hydride with an unstable one. On one side, you have the pure lanthanum hydride, which is extremely stable and possesses an equilibrium pressure very low at room temperature, 10 to the minus 29, which cannot lead to practical application. On the other side, you have the nickel hydride, which is unstable, leading to high equilibrium pressure, 10 to the fourth, at room temperature, which is also unpractical. And as you can see from this graph, the richer is the alloy in nickel, and the less stable is the hydride. And eventually, one formulation of lanthanum nickel 5 can absorb hydrogen at nearly ambient condition, which make it very interesting for hydrogen storage applications. So let's have a look on the structural properties of these compounds and where the hydrogen atom can sit within the structure. So it will go in the tetrahedral site. And in the structure, three different environments of tetrahedral are present. One with two lanthanum and two nickel as apex, one with one nickel and three lanthanum as apex, and one with four lanthanum. And in this space group, four crystalline space crystalline sites are available. One lanthanum 2 nickel 2 at weak of position 6M, two lanthanum nickel 3 at weak of position 12N and 12O, and one nickel 4 at the weak of position 4H. And now if we have a look at the multiplicity of the site, one can expect 34 hydrogen per formula unit. But in reality, only 6.56 are occupied, which is about 90% of the site occupancy. And this is due to geometrical and electronical criteria. To exemplify, if if we take the structure, and if we take the LAN3 tetrahedral 12N and 12O, the geometrical constraint impose an internal diameter of the site larger than 0.4 angstrom. And the electronical constraint impose a minimal distance of 2.1 angstrom between two hydrogen. Okay, interestingly, experiments have demonstrated that there is a linear dependence between equilibrium pressure and the cell volume of AB5 structure type. Therefore, if you want to adjust the value of the equilibrium pressure using a solid solution, thanks to the Vegard law, the value of the substitution can be easily determined. For instance, if we want an equilibrium pressure of 4 bar, by substituting lanthanum by yttrium, we will need a substitution of about 0.1 yttrium. The same hold for other kind of substitution. Therefore, we can finely tune the equilibrium pressure for this kind of systems. This is very convenient. For example, if we want to couple hydrogen storage material with an electrolyzer upstream at 25 bar and a fuel cell downstream at 1 bar, we can easily find the optimal formulation to satisfy these conditions. So let's compare now different metal hydride. The pressure and the temperature are rather low for this metal hydride, but unfortunately, the gravimetric capacity are also quite low. But the volumetric capacity are very high for this kind of material, which means that they can absorb a lot of energy in a small volume. For comparison, for high pressure hydrogen storage at 700 bar, the volumetric capacity is 39 grams per liter, which is lower than metal hydride. This means that these materials are prone for stationary hydrogen storage, for which the mass is not a problem. And industrial development have been made based on AB5 alloy, allowing to safely store high amounts of hydrogen in very small volume. So quickly now I'm gonna present you another energy storage method which I was working on, which is based on metal hydride, which is heat storage. So this method consists of gathering the intense sunlight onto a receiving tower here. So the strong heat generated must be stored and recovered to boil water to generate steam, to rotate the turbines and generate electricity. So nowadays, molten salts are used for this purpose, but metal hydride would allow to store much more energy. Indeed, as we have seen, metal hydride can reversibly absorb and desorb hydrogen, exchanging high amount of heat with the external environment. So during hydrogen desorption, the metal hydride, the heat is stored. During hydrogen desorption, the heat is stored because it's an endothermic reaction. And during hydrogen sorption, the heat is recovered because it's an exothermic reaction. So for this application, we need a stable metal hydride because of the high temperature in the receiving tower, such as magnesium hydride or magnesium iron hexahydride, which are very stable at high temperature. So by performing pressure composition isotherm, one can establish the pressure temperature diagram, allowing to determine the operational condition for such a system and choose the working hydrogen pressure to hold in order to cycle between high temperature to store heat and low temperature to recover it. So we have developed a demonstration tank as a proof of concept based on 5 kilograms of magnesium iron hexahydride, which is highly stable. And with this system, it was possible to store it up to 550 degrees C, which is very high temperature. And the storage amount was several orders of magnitude higher than the usually used molten salt. Let's have a look on another application of metal hydride using nickel metal hydride battery. Briefly, the battery is based on the electrochemical reaction. And as you can see, the metal hydride can also be obtained from the metal through a reduction, or the metal hydride can be dehydrogenated through an oxidation. So during discharge, the metal hydride is oxidized to form the metal at the negative electrode, while at the positive electrode, the nickel oxyhydroxide is reduced to form nickel hydroxide. And one electron is transferred during the process, and to balance the electron flow, hydrogen is transferred between the two electrodes in alkaline electrolyte. So using AB5 hydrides like lanthanum nickel 5, we can store up to 6 H hydrogen per formula unit, which lead to very high capacity. For instance, 370 milliampere hour per gram for lanthanum nickel 5. And the first time this alloy was proposed as negative electrode was in 1970. But unfortunately, this formulation was not optimized. First, because the equilibrium pressure, as we have seen before, is 1.7 bar. Yet a battery should work in normal condition of pressure and temperature. Therefore, the hydride will decompose at ambient pressure and temperature. So as we have previously seen, for this compound, the equilibrium pressure can be adjusted using substitutions. Moreover, this formulation, lanthanum nickel 5, is prone to decrepitation during hydrogenation, which lead to mechanical stresses, which is detrimental for the electrode. Finally, lanthanum nickel 5 easily form an hydroxide in alkaline metal. So hundreds of new formulations were published to solve these problems. And it turned out that the optimal composition is the following, with a mesh metal as the rare earth part. So misch metal is the natural alloy of rare earth, which is a mixture of cerium, lanthanum, neodymium, and traces of other metal. And this was very interesting result, as misch metal is cheaper than lanthanum because it's the natural alloy. And so it was proved that the presence of cerium improved the storage reversibility, and the cobalt improved the cycle life, while the manganese and the aluminum allow to adjust the equilibrium pressure. So now let's have a look on another kind of hydride, the so-called complex hydride. They are of high interest for hydrogen storage because of the extremely high gravimetric and volumetric hydrogen content as compared to other methods of storage. Therefore, they are promising candidates for onboard application, which need high gravimetric capacity. For instance, the most appealing complex hydride are borohydride, due to the extremely high hydrogen content here. And hydrogen from borohydride can be released either by hydrolysis, which is the reaction between the hydride and the protic hydrogen from the water to form hydrogen gas, or by thermolysis, meaning that the hydrogen is formed by thermal activation following this main reaction. But for practical application, only the first part is used because the metal hydride here is very stable and hard to be dehydrogenate. Unfortunately, some side reaction occur during the thermal treatments, leading to the formation of dodecahydrocloso-dodecaborate anion B12H12 2-, which is a cage of boron and a thermodynamic sink, meaning that no coming back to the initial borohydride. In addition, some diboron is formed to a certain extent, which is a toxic gas and detrimental for the reversibility. So despite the promising future as hydrogen storage material, borohydride are not very suitable for practical application, first due to too high operational condition, pressure and temperature, diboron impurity during hydrogen release, and poor reversibility. And as you can see here, borohydride decompose at very high temperature, above 300 degrees centigrade for most of them. So many researches have been done in order to reach reversible hydrogen storage system based on borohydride in mild condition by modifying the thermodynamic and or the kinetic. So in that respect, three approaches can be envisaged: the nanosizing, the use of additives, or the chemical modifications. So with respect to the chemical modification, a lot of mixed cation on or anion were tested, leading to a substantial decrease of temperature of their hydrogenation. And interestingly, there is a linear relationship between the electronegativity of the cation and the temperature. Unfortunately, this decrease in stability goes with an increase of diboron emission. Now, regarding the nanosizing, combined with additive effect, a very interesting system was found based on nanoparticle of lithium borohydride decorated with nickel nanoparticle supported on graphene. A substantial decrease of hydrogen desorption temperature was found, and a fully 9%, fully reversible 9% of hydrogen with an exceptional cycling stability over 100 cycles was also demonstrated. But unfortunately, such complicated system is hard to envision for practical application, but it's very interesting for scientific perspective. Tailoring the thermodynamic of the borohydride can be also achieved using reactive hydride composite. So the composite is obtained by finely grinding two hydride, complex or metal, in order to destabilize both hydride by forming a different decomposition product. And the enthalpy difference between the initial and the final step of the intermediate product should be smaller than the decomposition product of the hydrides, the sol hydride. So this approach has been intensively studied, and it's simple, and number of reactive hydrides have been published, which have led to reversible hydrogen storage system in milder condition than the sol complex hydride. For instance, for lithium borohydride, some reactive hydrides such as magnesium hydride or magnesium nickel hydride form interesting high content reversible hydrogen storage system. And for the formation of the thermodynamic sink, here B12H12, lithium B12H12, can be prevented with the appropriate catalyst. However, the systems are not stable upon cycling owing to particle aggregation and side reaction detrimental for the cycling stability. But this approach is very promising, and more effort must be done in that direction. So I will switch now to another application of the complex hydride because we have seen that the borohydride, the decomposition product of the one side reaction of the decomposition product of the borohydride form the B12H12, chloroborine. And interestingly, this thermodynamic sink was found to be a tremendous solid-state ionic conductor for all solid-state battery. So first, what is a null solid-state battery? So it's a battery in which all components are solid, even the electrolyte, which allow the ion transfer from the positive to the negative electrode, which is usually liquid. So in the lithium-ion battery, this liquid is highly flammable and can lead to safety issue. So what are the advantages of a solid-state batteries? So first, the safety issues, there is no safety issues. After the solid electrolyte, in the solid electrolyte, the transference number is close to unity. But what is the transference number? So it is the net rate of positively charged ion traveling from one electron to another. Indeed, even though usually the cation diffuse faster than the anion in a liquid electrolyte, nothing prevents the anion to travel in the other direction, which leads to a strong polarization within the electrolyte and overheating. That is one of the reasons that the battery cannot charge very fast to avoid this phenomenon. And in a solid, the anion would not move so much. In addition, usually the solid are more stable and they allow a more compact design. And also there is less metal leaching in the liquid electrolyte because it's a solid. And there is no self-discharge of the solid because it's more insulating than a liquid. But in the cons side, solid have lower ionic conductivity, they are more expensive, and the ionic contact between the electrolyte and the electrode is poor, and some mechanical stresses could appear due to volume changes upon cycling of the electrodes. So, and I told you sodium B12H12 was found to be a solid electrolyte with superionic conductivity with 0.1 Siemens per centimeter at temperature above its phase transition from a monoclinic to a cubic phase. For comparison, to be competitive with a liquid electrolyte, the ionic conductivity expected is in the order of millisiemens per centimeter, but at room temperature. So this finding has led to intensive research and to decrease the temperature of the phase transition. And we have found that this mixed anion formulation, B10H10 and B12H12, can meet the expected ionic conductivity at room temperature. However, these mixed anions were obtained by solid-state chemistry, which leads to poor ionic contact between electrodes and electrolytes. They are expensive, and the synthesis of the precursor brings into play some toxic boranes. So the challenge was to develop a cost-effective synthesis without any toxic boranes. So to obtain the electrolyte from solution, therefore, we have developed the following new routes to elaborate the electrolyte from isopropanol. which enable us to infiltrate porous electrodes with a solution of the electrolyte, leading to increased ionic contact and good cycling capacity. The last family of complex hydrides that I'm going to talk, which has been envisioned as material for hydrogen storage, so now I go back to hydrogen storage, are the aluminum hydrides, and particularly sodium aluminum hydride. So despite its lower hydrogen capacity as compared to borohydride, it benefits from favorable thermodynamic and kinetic properties, with 5.5 weight% of reversible hydrogen content in practical conditions. It decomposes in two steps. In two steps. So the first step to give the sodium aluminum hexahydride and releasing 3.7 weight% of hydrogen, and the second to form the sodium hydride and aluminum with 1.8 weight% of hydrogen. So sodium hydride being too stable, the decomposition cannot go further. So for now, this material is more prone for industrial development than borohydride because they can reversibly store hydrogen in mild condition. Therefore, a lot of research that have been done in that sense with development of demonstration tank based on sodium aluminum hydride. However, hydrogen storage system based on sodium aluminum hydride require appropriate quantitative kinetic description for simulation and design principle, in particular for the crucial absorption process. So how to derive the kinetic description from experiment? So the net rate of a reaction of the absorption state is defined in terms of rate constant and G alpha, which is a function of the transform fraction. The underlying kinetic process of the absorption, and especially the rate limiting process, determine the rate of the reaction and consequently the function G alpha. So in practice, the function G alpha is obtained by empirically fitted the transformation fraction as a function of time with the integrated equation of different kinetic models. Once a proper model is chosen, the next step is to determine the rate constant and the activation, which are the parameters of importance to feed in the simulation. Here, an assumption must be done on the function f, which reflects the influence of the pressure applied and the equilibrium pressure on the net reaction rate. Usually, f is described as shown here, but can have a slightly different form. Once a model is found and validated, one can draw the pressure temperature diagram, the rate constant for every operational conditions. And the dot line here represents the maximum rate of the reaction for every pressure. So these results are very useful to determine the optimal conditions and for modeling the behavior of the material during hydrogen cycling in the tank. So now in conclusion, so in this lecture, we have seen that metal hydride are a family of materials that can safely store hydrogen in mild condition. Interestingly, the equilibrium pressure can finally adjust by appropriate substitution, and there is a strong correlation between the structure and the property. For this family of hydride, industrial applications such as stationary hydrogen storage or nickel hydride batteries are already existing. I have shown you that stable metal hydride can be also envisaged as material for heat storage application. After we have seen another family of hydride as promising material for hydrogen storage, namely the complex hydride with ultra-high hydrogen storage capacity. However, for this family, the thermodynamic is not favorable. Indeed, a covalent bond has to be broken and form, which is more difficult than interstitial hydrogen absorption or desorption in metal hydride. However, because of the high capacity, a lot of research have been done and have led to significant improvements, but progress must be done. And finally, I have shown that a compound that was found to be unwanted because of its thermodynamical stability, namely the chlorohydroborate, okay, I think something went wrong. And you may have.
Thank you so much, sir, for such wonderful lecture. You gave all of us really interesting information about the hydride-based energy storage material. I guess there is a question in the chat box. Sir, may I ask you the question? Am I audible to you, sir?
Hey, sorry, something went wrong, no? Oh, I think
Am I audible to you, sir?
Sorry?
Sir, I was saying thank you so much for such wonderful lecture.
Thank you, but everything went good because I think the connection is not good.
Sir, I have a question in chat box.
Okay.
Yeah, which hydride material is more suitable for hydrogen storage in terms of cost and environmental sustainability, in your opinion?
Okay, so good question, thank you. I think we can go for hydride, which are very abundant for like magnesium hydride, because they have high, let's say, high hydrogen gravimetric hydrogen content and high volumetric hydrogen content as well. But the thermodynamic of magnesium hydride must be also tailored to lower the operational condition, because the operational condition are maybe a little bit too high, the temperature and the pressure. Compared to the hydride that I've shown you before, like lanthanum nickel 5, which can be hydrogenate and dehydrogenate at very at ambient conditions. But because it has like lanthanum inside and nickel also, it's not very environmental friendly.
So what do you think, how much time it will take to reach this hydrogen storage technology to masses, especially for the developing countries which are really struggling for energy? They are facing energy crisis. So how much time do you predict it will take to reach that technology to common people?
I don't really know, but I think hydrogen storage, we can already store hydrogen. So we can use hydrogen technology today, because even though if it's dangerous to store hydrogen at 700 bar, we can still store hydrogen. But we need to improve. So we have a little bit more time, let's say, to improve the technology. I cannot give you very a timetable of the development of this technology, but I think metal hydride are very close to be almost ready for hydrogen storage purpose, and some industry already developed this technology, so it's okay. For the complex hydride, I think it's more far away.
Thank you so much, sir. Thank you so much for sharing your expertise with all of us. Thank you so much, all the participants, for joining this lecture. I have shared one feedback form here, link. You can click the link and give us the feedback. Thank you so much, Dr. Romain, Moury, sir.
Okay, thank you very much for the invitation.
It was a pleasure, sir.
Thank you.
Thank you all.
Bye.
Yes, sir. With this, I declare the end of this lecture. Goodbye, everyone.